Hey, what's going on, guys? So today I'm going to be talking about physics and mathematical physics in particular, as a field that's it's really unifying mathematics and physics together. Um, and the reason why this is kind of its own convergent thing, and why really introducing physics and mathematics is they're inseparable from each other. And we arrive at this conclusion from a series of arguments. But what we first need to do is take a look at the structure that we've built. Okay, so we built a continuum. Um, we constructed real numbers from nothing, and then we forged the tools of analysis to measure change. Then we built algebra. So we stripped away the coordinates and discovered the invariant structures like vector spaces and Lie groups and symplectic forms that exist independently from our point of view. Okay, and then the last video where we concluded, really, I guess, at the edge of mathematics itself, at the monster group, right, where we had representation theory, which was that symmetry can generate space. And we built geometry, right? We allowed space to bend, twist, tear, discovered manifolds, cohomologies, and rigid laws of Riemann surfaces and complex analysis. Okay? But we built a stage, right? And it's empty though, because there's no script that governs it. Geometry without any motion on it is just a sculpture, right? So mathematics constructs the sculpture, and physics dictates the script at which this sculpture is allowed to, be dynamic, right? And so this is a little bit of a taste of what exactly physics does. This is not really a physics video where we're going to derive laws from experiment or intuition. We're going to actually derive physics from geometry, okay? And we're going to see that the laws of nature, so conservation of energy, gauge invariance, the existence of antimatter, the quantization of charge, are not arbitrary rules written by some deity, right? They're inevitable mathematical consequences of the geometric structures that we've already built, okay? So what we'll look at is we're going to basically climb this ladder of physical abstraction, from classical ideas of particles to the edge of quantum gravity. So we'll talk about symplectic mechanics we'll start by fixing classical mechanics, strip away any like Newton's apples and masses, and we're going to reveal that phase space, Hamiltonian phase space, is the symplectic manifold, and that energy conservation is the geometric preservation of volume under flow. Next, we'll talk about connections on something called principles bundles, and they reveal the true nature of force itself. So electromagnetism, the weak force, the strong force, they're not vectors. They're actually curvatures living on a principal bundle. And a potential is something called a connection, or a rule for comparing values at different points. Okay? And then quantum mechanics is going to be defined by Poincaré representations. So instead, what is a particle? We need to figure out what is a particle, right? It's not a tiny ball. It's an irreducible representation of the symmetry group of space-time. So mass and spin, these quantum mechanical objects are just simply the labels of this representation, okay? The next thing we'll talk about is statistical field theory and renormalization. We're going to confront the infinite. And quantum field theory is plagued with infinities because we assume that it holds at all scales. So the renormalization group explains how physics changes as you zoom out, revealing why the universe has stable phases of matter. And then the last thing we'll talk about is more avant-garde, which is geometric quantization. And we're going to attempt basically the ultimate unification. We're going to show how classical phase space, we're going to turn the mathematical way of representing classical phase space and transforming it into a quantum Hilbert space. And we'll see that quantization now is not just some algorithm that we, do, but it's a cohomological obstruction. The number then of quantum states in the universe is determined by the topology of the phase space itself. And this will be kind of the end of the line. No more approximations, and we're not just going to write the laws from the geometry itself. So we'll begin our reconstruction of physics first by stripping away the Newtonian baggage. In classical mechanics, you are taught that force equals mass times acceleration, right? F equals ma. You are taught that energy is conserved, because it is, right? You're taught that differential equations, you can solve them using coordinates and determine, the future up to an infinite amount of time, right? Okay. But in chapter 3, remember, we built manifolds, and we built a world where coordinates are arbitrary artifacts of our perspective. So if the laws of physics are fundamental, they cannot depend on whether we use Cartesian or spherical coordinates. F equals ma is not a geometric statement. It only holds for specific inertial frames. So we'll need coordinate-free. We'll need a formulation of mechanics is said that is coordinate-free. And we need to realize that phase space, Hamiltonian phase space, is not just a container for particles. It is a fundamental dynamic geometry that is a symplectic manifold. We're going to then, rebuild classical mechanics from the ground up, and we're going to discover that energy conservation is not an axiom. It is a geometric theorem. We will see that symmetries, or Noether's theorem, are generated by a map called the momentum map. And we will find that integrable systems, solvable problems, in other words, are actually tori in disguise, okay? They're topologically equivalent to toruses, or tori, whatever you want to say, all right? So let's start first by defining a manifold Q. And it's an n-dimensional manifold that we'll call configuration space, or just positions. You can think about this as representing this all possible positions of a system. So, for a particle in R3, right, Q would then be, R3, right? So for a pendulum or something, the mechanics would be restricted to a circle. And so the configuration space would then just be a circle, S1, topologically a circle. And for a rigid body rotating in space, the configuration space is actually just the entire rotation group, SO3, all right? So that's how you can think of this. And that's great, but dynamics requires velocity, right? We need to know where the system is going. And so you might think that we should have, we should take a look at the tangent bundle, which is the space of positions and velocity vectors. But there's a subtle problem, because in the deep geometry of physics, momentum is actually not a vector. Momentum is actually a covector, all right? So the reason why this is because the object that pairs with velocity to give energy, a scalar, right? So again, momentum gives us energy. And since energy is a scalar, momentum again is a function of velocity. So since energy is a scalar and velocity is a vector, momentum must be the dual object, or the function of that object living on a dual space. So therefore, the natural home for mechanics is actually the cotangent bundle, if that makes sense. And this space has local coordinates, Q1 to Qn, and then P1 and Pn, right? And it has dimension 2n, okay? So essentially the canonical 1 form, the Liouville form, theta, this is the space that comes equipped with a special geometric object, the Liouville 1 form theta, and it intrinsically, theta sub alpha v, right, in the coordinates takes a incredibly simple form, which is that theta is equal to the sum of the momentum dq, okay? And this p dq kind of term here is seen, it's very familiar, and it's seen as something called this principle of least action. It exists naturally on the bundle without any specific choices. So the symplectic form then, you can find this by taking the exterior derivative of this 1 form and get, again, this symplectic form. And that's essentially how you would represent the exterior derivative. And so this but this here would give us there's different sign conventions for the symplectic form. So again, you can look at this being positive or negative, but again, just remember it's for symplectomorphisms, you are what gives the quality of the symplectic space its tensor algebra is the symplectomorphisms that preserve the sign volume. Okay, because this 2 form here is going to allow us to create the engine of mechanics. It will allow us to measure the area of phase space. And unlike the Riemannian metric, ds squared, which measures a distance and has local curvature, the symplectic form itself is fundamental because it's locally flat. And Darboix's theorem here tells us that every symplectic manifold looks exactly like dp dq, wedge dq, if you zoom in close enough. And this means that there's no local gravity in phase space. The local geometry of dynamics is universal itself, okay? And so, again, we can go through the examples for configuration space and find that the cotangent bundle is actually R6. And so with standard coordinates, we can then have that the symplectic form can be represented in this way. We can also look at a rigid rotor where the configuration space is just the special orthogonal group, which then gives us that the cotangent bundle on SO3 is diffeomorphic to SO3 cross R3 via something called the left trivialization. And the canonical symplectic form in angular momentum coordinates is L1, L2, and L3. And this is the Kirchhoff constant Serow form on coadjoint orbits. So that sounds like a big word salad, but essentially you can just solve rigid rotor problems with this simplified geometric, more fundamental way of thinking about it. There's also the pendulum. So if you have the configuration space to be S1 with some angle theta, the cotangent bundle of that acting on that configuration space gives us S1 cross R with these coordinates. Okay, and so that's great. But now, how do things move? Okay, in Newtonian mechanics, you need a force vector, right? You need something that's gonna describe some, like, you draw your force diagrams in high school or whatever. But in symplectic mechanics, you actually just need a scalar function, and it's called the Hamiltonian. So for H will represent the total energy of the system, and that'll allow us to describe movement of things. So the symplectic form will act like a machine, and it takes the gradient of the energy, so dH, it takes the gradient of the energy, and it twists it into a vector field, x sub h, okay? And this is the geometric version of Hamilton's equation, okay? And so again, let's verify this in coordinates. So if if the symplectic form is dq cross dp, and the gradient of the energy is del h del q del dq and del h del p dp, the equation iota of the flow of that, or sorry, the equation iota of the vector field, right, forces the vector field to be essentially conservative or exact, in other words. So if you read off the components, then the velocity is equal. The velocity itself is equal to the change of the change of the Hamiltonian with respect to the momentum, and the change of the Hamiltonian with respect to the coordinates gives you the force. Okay, and this allows us essentially to recover Hamilton's equations, but now we see them for what they physically are. They are the symplectic form rotating around the gradient by 90 degrees. Okay, so instead of of flowing down the energy slope, right? Like a ball rolling down a hill. The system itself is going to flow along the contours of constant energy. Okay? And what this allows us to do is, since again the symplectic form is antisymmetric, right? So if something's antisymmetric, that means if I took the symplectic form and gave it the same vector that's always 0, right? The energy conservation is not an assumption. It is a consequence of the antisymmetry of the symplectic geometry itself. Okay? So that allows us then to describe the conservation of the conservation of the symplectic form. So if we look at a free particle, then the Hamiltonian p squared over 2m on the tangent bundle of R3, then we could have for the field p over m times del q, okay? And this would be if the flow itself would be a straight line motion of q parameterized by time, and also p of t would be constant, okay? And so that would give us the geometry of the flow itself. If we looked at harmonic oscillator for n equals 1, the solution is, again, gives us cosine and sine, and we can arrive at the harmonic oscillator, or the solution to it, on the phase space. And we can also look at the Kepler problem as well, where the cotangent bundle acting on R questioned out by the 0 point, or the point at 0, right? What this gives us is a Hamiltonian vector field, again, that has trajectories as conic sections, and Bertrand's theorem guarantees closed orbits only for harmonic and 1 over R potentials in general. All right, and so this gives us the central force or Kepler problem as well. All right, so that's great. Let's look at the Poisson bracket. So we can abstract the structure into an algebra, and the Poisson bracket measures how one observable changes along the flow generated by another one. All right, so let's say we have a Poisson bracket of f and g defined on the continuous cotangent bundle of the configuration space. Okay, assuming that it's infinitely differentiable. Then in coordinates, we could define the symplectic form of these two fields in coordinates as such, okay, in general. And this bracket will govern the time evolution for any observable f. All right, and so the time evolution then is defined as this. And remember, we have the bilinearity of the Poisson bracket. We have the Leibniz rule, and which describes, again, the derivation, and the Jacobi identity, which gives us this the cyclicality. Okay, and we have a theorem which states that the structure on the Lie algebra space of functions eventually is extremely important, because the Poisson bracket will be 0 if and only if it's conserved on the flow of H, and this will give us then the fundamental brackets. So this is exactly what Dirac would later identify as a precursor to quantum mechanics, because in order to quantize anything, we need to simply replace the Poisson bracket with the commutator. All right, and we would be able to do this for operators. So if we look at example 1 here, we would say that the angular momentum is equivalent to the Levi-Civita times the contraction of the coordinates and the momentum, and the dual computation yields as such, and this gives us the SO2 algebra. Okay, it gives us the Lie algebra for special unitary matrices, SU2, and this becomes isomorphic to the SO3. All right. Also, the Runge-Lenz vector for Kepler. This is a conserved quantity that comes from mechanics, and we can also have it as if we have we can verify that the Poisson bracket will give us the Runge-Lenz vector, giving us that secret a conservation law here that shows that this particular choice of a vector it has a Poisson bracket that's equal to 0 with the energy. Okay. Now let's look at momentum maps. We've really come now to the deep connection that symmetry and conservation are connected in some way. So if you assume over a configuration space Q that it has a symmetry group G, like some rotation SO3 or some just diffeomorphisms in general, this leads this group action lifts to the phase space. It lifts to the phase space of that's defined by the cotangent bundle of the configuration space. And for every generator, let's say Z of the Lie algebra, there's a vector field on the phase space that generates that symmetry, and we can define a map of the cotangent bundle onto that particular Lie algebra star, and this gives us the momentum map that's defined by the relation where we have a metric essentially, or we have the differential of this form from J and epsilon, or sorry, J and C are equal to, again, this this measurement on that infinitesimal generator. Okay, and so this is a geometric kind of realization of Noether's theorem, because we can say that, well, the map itself is conserved for any energy invariant under the group action, and essentially it states that if the Hamiltonian, again, is invariant under the symmetry group, then the function J is conserved along the Hamiltonian flow. So we can look at some key examples like translation symmetry, which says that if we have the group action acting in 3 dimensions, the generator, for some generator A and the map P dot A, well, the momentum map J, which is linear momentum, and the components J sub I, which is linear momentum, essentially tells us that if the system is invariant under shifting from some Q to Q plus A, right? That would be your generator, just the plus A in general. The conserved quantity is linear momentum. All right, and the same thing for a rotation symmetry, which let's say the group is the special orthogonal group. The system is invariant under the rotation and is conserved under a quantity called angular momentum, which is defined as the cross product of Q and P, the coordinates and the momentum. All right. And then if we look at time translation, this tells us if physics doesn't change with time, the conserved quantity is energy, or H. So the group of the real numbers acting trivially on the configuration space, if the lifted action leaves Q fixed, then it adds a multiple of dq to covectors, and again, the momentum map is H itself. We also have Galilean boosts, which tell us that if we wanted Q to Q plus Vt, the momentum map would be P minus mvt fixed at T, and the components would then give us a center of mass motion. So essentially, Galilean boosts themselves, doesn't matter if you're going a certain speed. There's a particular conservation law that's fixed, okay? And this is interesting because you can derive kinetic energy from this via Taylor expansion. All right. So again, we can show that the momentum map will unify all of these conservation laws into really a single geometric object, and conserved quantities are simply the generators of the symmetry that preserve the system itself. So again, if the Hamiltonian is invariant under the action, then its Poisson bracket is equal to 0, and the momentum map is conserved along the flow. Now this brings us to Liouville's theorem, which says finally what happens to a collection of particles, or in other words, a statistical ensemble. That's all that is. A statistical ensemble is just a collection of particles, and since the Hamiltonian flow preserves the symplectic form omega, it must also preserve the volume form omega. Minus 1 in times n minus 1 over 2 over n factorial times the symplectic form to the n, based off of the number of particles there are. And since, again, it preserves, the preservation then can be shown that the Hamiltonian will preserve the phase, preserve the phase-space volume under any symplectomorphisms, which means that the flow of the mechanical system acts like an incompressible fluid. You can actually stretch a cloud of states. You can twist it into a fractal spiral, but you can never compress it. And information is never lost. It's only scrambled. And this is basically the foundation of statistical mechanics and entropy itself, okay, via Liouville's theorem. So a consequence of this is that statistical ensembles with uniform density on energy surfaces remain uniform. And if we look at a harmonic oscillator where the orbits are ellipses in coordinates and momentum plane, the area is conserved. And this recurrence and ergodicity on energy surface is a defining feature for harmonic oscillators. And this allows us to describe Einstein solids as well. I'm just trying to show you that all the physics that we learn in undergraduate is inherently can be derived just from geometry, okay? So geometry obviously is this much more fundamental object that defines all of the laws that we've found so far, all right? So while integrability, most systems are very chaotic, some are integrable and perfectly solvable. And what we can say is for a system with n degrees of freedom, it would be said to be Liouville integrable if it possesses independent constants of motion, F1 through Fn, where F1 is equal to the Hamiltonian, okay? And there's also some that are involution. That means that all their Poisson commute with each other, and so they are in involution with each other, okay? So all of those independent constants of motion, or integrals of motion, if you will. So the Liouville-Arnold theorem says that if a system is integrable, the level sets of these constants are not just random shapes, they're actually diffeomorphic to tori, okay? And the motion restricted to wrap around these donuts forever in quasi-periodic lines is the defining feature of this. Okay, so for a free particle, it's, well, we'll show this in a second, but essentially the level sets are in tori, and they exist as these action variables, or these integrals, such that they are functions, or these constants are functions of this integral with the conjugate variables, okay? And again, this is quasi-periodic linear flow, and we can change the coordinates to action angle variables, where the Hamiltonian itself is a function of the action, and theta dot is equal to a constant. So we can look at, again, isotropic harmonic oscillators in the real numbers within n dimensions. So we'll have a Hamiltonian that's defined by just a bunch of oscillators, and the additional integrals here are all pairwise commutative, so the level sets are in tori. If we look at the Kepler problem, angular momentum and energy and the Runge-Lenz vector, these would be three different components, and all five independent commuting integrals after removing relations generate tori. You can also look at the 1D total lattice. So for three particles, the Hamiltonian looks like this, and the Lax pair construction will yield additional integrals from trace powers of the Lax matrix. So again, this explains why planetary orbits are stable and predictable over billions of years, because they are locked into invariant tori in phase space, and chaos really only emerges when these tori break down. This is called KAM theory. All right, so again, treat this as a survey. Treat this as kind of like a little bit of infotainment, I guess, if you will. But essentially, we've completed and successfully rebuilt classical mechanics because we stripped away the coordinates and found a symplectic manifold as the sage itself. And we also found that Hamilton's equations are the flow of a vector field generated by the symplectic form omega. And we also found that Noether's theorem is the existence of a momentum map. Okay, so Noether's theorems can be employable if you have a momentum map. And we also found that orderly solvable motion corresponds to geometry on a torus. But we've only really described motion of particles, so now what we need to do is describe the motion of fields, okay? And in the same way that you might, derive these things, I don't know if you guys have worked through Landau's classical field theory and classical mechanics books, but this is kind of how he does this when he first constructs classical field theory, which is looking at variations with respect to particles or the action variations with respect to that, and then we go into the fields. We're gonna do the same thing here. So now what we're gonna say is we need the motion of fields and we gotta describe force. So we'll see that electromagnetism, the weak force and the strong force, are not just vector fields, they are inherently geometric creatures or curvatures living on higher structure called principal bundles. Okay? And so, again, we rebuilt the mechanics of particles previously, right? And we found that matter will move along, these like contours, which is interesting in and of itself. And these contours belong to a symplectic manifold. But matter is not alone. It is pushed and pulled by forces. So gravity, electromagnetism, the weak and the strong nuclear forces. In classical physics, we will treat these forces as vectors living on space-time. So we would say, the electric field is a vector, the magnetic field is a vector. But this is really a lie. Because if you describe the weak force as a vector, the math will break, right? It's really like vector minus axial vector. Okay, so if you want to describe gravity as a vector, you're going to get contradictions as well using this. So to understand force, you must ascend to a higher geometric structure. Force is not something that lives in space, but it's the curvature of a structure that lives over space. And this structure is called the principal bundle. So we're going to unify all of the known forces of nature from a falling apple to a gluon, okay, into a single geometric definition of the principal bundle. And this will allow us to then describe potential as just corresponding to a connection on this principal bundle, and a force, again, as a curvature on that connection. And so, again, electromagnetism, the weak force and strong force and gravity, they belong to particular symmetry group structures. Okay? So, if we look at this, we can use the idea of a vector bundle. Okay? And that's where you attach a vector space to every point in the universe, like a tangent bundle. And you can treat this kind of like hidden dimensions. Because the principal bundle is different. Instead of attaching a vector space, we can actually attach a Lie group. All right? So, we're going to define a principal G bundle over a manifold M. It is a fiber bundle where we map from P to M, okay, with a free and transitive right action on the Lie group G on each fiber such that locally P is trivial, so that the inversion of that fiber bundle onto the P is isomorphic to the for an open U on the manifold. Okay, so we take some open set on the manifold and take the product of that with the Lie group, okay, acting on each fiber. And this is said to admit a local trivialization. The fiber is the Lie group itself, and there was a free and transitive right action on each fiber. And locally, P, or the fiber bundle, or the map from P to the manifold, looks like U cross G. All right. On overlapping charts, let's say we have some U alpha and U beta, we can relate the components by a function, which will say G sub alpha beta, right? Where we have the overlapping charts mapping to the group itself, and they will satisfy something called the cocycle condition. All right, where if we take G sub AB alpha beta times G sub beta gamma, we'll get G sub alpha gamma. Okay, and so that's cocycle condition. So again, if we look at the trivial bundle, so the bundle P is equal to the essentially the manifold across the group structure. In physics, that corresponds to the vacuum state where global symmetry is possible. So for any G and M, the product bundle is a principle with the action M comma G dot H is equal to M comma GH, and the transition functions are constant 1. If we look at the frame bundle, okay, instead of the trivial bundle, the frame bundle is the set of bases for the tangent spaces of the manifold M, and the structure group, we would say the general linear group of the real numbers, acts by right matrix multiplication. So local trivialization over a coordinate chart makes the frames respect the differentiation under the coordinates. Okay. We can also have oriented frame bundles. So if we reduce the frame bundle to the structure group of SON, we can choose oriented bases. There's also something called the hop fibration, which says that the fiber bundles can be, or the space P can describe a map from the three, I guess, 4 dimensions, or technically this would be like the 4 sphere, or a hypersphere, onto the manifold to be embedded or to be equal to the 3 dimensions. So in other words, this group structure is equivalent to the isomorphism of the unitary group with the circle, okay, the space of unitary rotations, right, in the complex plane. And this is a geometric model of the magnetic monopole, right? So the hop fibration of itself is a geometric model of the magnetic monopole. And this bundle is non-trivial, and this is something we would say has a Chern class of 1. Specifically, that means that the points S3 are in Z1 and Z2 with the magnitude summing to 1. And that means that the fiber over the complex projective plane is the phase of e to the I theta, or e to the I phi. We can also have a Dirac monopole, which is a U1 bundle over S2 with, or over just the three-dimensional sphere, with the Chern number. And again, whenever we see the S2, you can think it's more generally referring to a topology, something that's topologically equivalent to a sphere, okay? And the Chern number k is in the integers. If k is equal to 0, the bundle is twisted and you cannot define a global potential over A. So it's non-trivial for k is not equal to 0. So that means there's no global section, which is an interesting construction, okay? But again, you can think of the fiber bundle or the principal bundle like this. Every single point in space-time, there's a tiny invisible shape attached, or a hidden shape, and it's in internal symmetry space. So this bundle P looks exactly like M cross G. Again, that's what the trivial bundle tells us, but globally it can be twisted, and it twists the topology. And the hop fibration, then the hop fibration here, mapping this is a non-trivial bundle of a circle over a sphere. Okay? So, in physics, we would call this a magnetic monopole. Every time that we take a non-trivial bundle of a circle over a sphere, in general. Okay? Now, we also have something called the connection. All right? And it comes from somebody, a mathematician named Erasmus, and what the connection tells us is if we imagine a particle moving through space-time, it's going to carry some internal clock with it, or some phase. That means that it would be an element of the group G, because that's what defines the phases, right? Over the projective, or just in general, that can allow us to define the phase by the group transformations of it. So it'll carry that internal clock with it, or a phase element of the group G. So how do we compare the phase at point A to the phase at point B? If the bundle is twisted, or keeping the phase constant, keeping the phase constant itself is ambiguous if it's twisted. So we need a rule, and we need to define the connection. So we'll say an Erasmus connection is a geometric rule that separates motion into two types. So vertical motion is moving up the fiber. So if we're changing the phase without moving in space, or horizontal motion would be moving along the bundle, moving in space while keeping phase constant. Okay, and essentially what that allows us to do is mathematically describe a connection one form. But if we choose a choice of that horizontal subspace at every point on P, such that when we take the direct sum of the horizontal subspace with the vertical, with the vertical being the kernel of the exterior derivative of the bundle being isomorphic to the vertical to the Lie algebra, okay, what we can have is that the vertical tangent bundles are fundamental vector fields, okay, or the raising musical isomorphism, and that connection would be G. It would be said to be G invariant, where we would have the Ricci curvature tensor over that defined by that particular Lie algebra or Lie group, okay, in terms of this indice, okay. So this allows us then to define a connection one form, which tells us it's a one form A that is valued in the Lie algebra G, and what that does is it's going to eat a velocity vector and spit out a matrix, essentially. And so that's essentially what we have. So if we have the potential of the musical isomorphism of the generator should be equal to generator for any generator that belongs to the algebra, and it acts on the identity of vertical operators. And then the add valued action on the potential itself will be equal to that curvature tensor, okay, of the potential of the connection one form itself, okay. This would transform it directly under the group action, and so the horizontal vectors V, should obey it, such that if we put horizontal vectors into the connection one form, that should give us 0, if that makes any sense, okay. So this is a very subtle definition, but it allows us to describe the rules that we need to separate vertical motion from horizontal motion, and moving along the base of the fibers, okay. So if we look at the trivial bundle again, the flat connection A is equal to 0, this is purely vertical. This gives us H to be equal to the tangent bundle of the manifold crossed with the 0, okay. And another common choice would be the connection one form as G inverse dg, okay. And this is called the Moyer-Cartan form pulled back, okay. If we look at the Levi-Civita on a frame bundle, so if you take a frame bundle acting on a manifold, the torsion-free metric compatible connection is uniquely determined. All right? And this allows us then to describe something called a local gauge potential. So physicists don't usually see the full bundle. We'll work in a gauge or a local slice. And when we see the connection form pull back to the base manifold, again, if we see the connection form pull back to the base manifold, we'll get the familiar gauge potential. So in a local trivialization, we'll call sigma sub A, where if we have the pullback on some U, some open set, sub alpha, some open subset of the manifold, and we cross that with the group choice. Okay, we can have P to map to X of G sub A of P, and if we define this local trivialization, the local connection 1 form would then be described as such. And in standard physics notation, you could just say the 1 form sub A of X would be equal to A mu of X times these 4 vectors here, which would give us would tell us that it's a differential form. That's a function of the Lie algebra and the particular open set that we're choosing. That's local, okay? And in this coordinates, this gives us the familiar gauge potential of physics. So, for example, we can have that essentially we really can have that electromagnetism EU or in U1, right? This is the vector potential itself, right? So we can recover the vector potential of from G being E, the generator E to the I lambda to be a generator inverse times dG, which will get I d lambda, okay? And if we also look at quantum chromodynamics SU2 would give us the term that as a nonlinear self-interaction required for the standard model or Yang-Mills theory. So the Lie algebra would be equal to SU2 for anti-Hermitian matrices, all right? And then the gauge transformation would allow us to take that it would allow us to take the gauge or the volume the connection 1 form, right, and describe some G of X that's within SU2 itself, okay, or the group rotation or the group actions themselves, okay. Now, if we look at the Levi-Civita connection on an oriented orthonormal frame bundle, if we have the special orthogonal acting on the manifold to map to the manifold with metric G, the local connection form, which is also antisymmetric, will give us its covariant derivative, or given that the covariant derivatives on the vector vanish for a metric and torsion, we can then, from the Levi-Civita connection, get the Christoffel symbols, which you can see in the tetrad formalism from from a local connection form. Okay. Now, again, these are all the same mathematical object, though. The connection 1 form. So now that we have potential, now that we have, now that we've successfully described potential and the mechanics of this, we now need to describe field strength. So what is field strength? Again, if A is the potential, what's the force? And force, again, is what happens when you try to parallel transport a particle, right, around a closed loop. And if the space is flat, the particle comes back unchanged. If space is curved, the particle comes back a little rotated or phase shift by phase. And if I try to transport a particle across a sphere in like a little circle or a triangle, it's going to come back a little bit oriented. It's going to be oriented a different way, or phase shifted. So we measure the failure of this with the curvature 2 form, all right, F. And the curvature 2 form, F, is the field strength tensor, all right? If we take it in coordinates, it becomes a field strength tensor, all right? So for local expression, the field strength is equivalent to just the exterior derivative acting on the connection 1 form times 1/2 times the commutator between the connection 1 form itself, taken horizontally. But if you're looking at local expression or the field strength in and of itself, that would be the exterior derivative acting on the connection 1 form plus the wedge product between the connection 1 form itself, right? Now there's a theorem called the Ambrose-Singer theorem, which tells us that curvature measures holonomial. So a parallel transport around a small parallelogram spanned by vectors u and v returns a group element 1 plus the connection 2 form, the curvature 2 form, plus higher order terms that depend on the area squared. All right. So if we look at an abelian, connection, curvature 2 form, where there's no commutator, the commutator value is 0, that's how it's abelian. Then we would just get that the commutator vanishes and we get electromagnetism. All right. But if we look at a non-abelian curvature 2 form, this field carries its own charge. So that actually the gluons will interact with gluons themselves. And so this allows us also to define the Bianchi identity, which just means that the boundary of a boundary is 0. All right. And so the derivative then of the curvature, right, the derivative of the curvature must also be 0. And this Bianchi identity, or this single geometric identity, generates half of Maxwell's equations. And the constraints of also general relativity, right? Because the Einstein field equations must obey the Bianchi identity. If we look at an example of an abelian group here, U1, it has no wedge term, right? So the curvature 2 form has no wedge term, but the Bianchi identity, again, is satisfied, which gives us the Maxwell's vacuum. If we look at a non-abelian version of the curvature 2 form, expressed from the potential 1 form, we can satisfy the Bianchi identity as such. Okay. The Hopf vibration monopole, the connection 1 form looks like this. It's 1/2 of 1 minus cosine of theta with respect to d theta on the northern hemisphere, and this becomes like a direct string gauge. If we look at a curvature 2 form to be 1/2 of the sine of theta, d theta wedged with d phi, to be equal to 1 over the exterior derivative of the volume form, or the solid angle, in other words, 1/2 or this is essentially the solid angle. If we integrate the flux, it would be equal to 2 pi, and the Chern number would be 1/2 per hemisphere, so we get a total of 1 after patching both hemispheres. All right, and that gives us the Hopf vibration monopole. Now, let's talk about characteristic classes. So sometimes the field configuration has a twist that we can't remove. So to detect these twists, we need characteristic classes. And these are integrals of the curvature that yield integers. So, for example, if we take Chern classes, and we've used Chern classes a little bit, but I'm going to properly define this here. These measure the twists of unitary bundles. So the first Chern number counts the magnetic monopole charge, and the second Chern number will count, instantons. So these are tunnels between different vacuums in quantum chromodynamics. There's also stuff called Poincaré classes on the special orthogonal rotations. And these numbers just measure the twist of orthogonal bundles. So essentially gravity, right? And essentially what these look like, and then there's also something called the Chern-Simons forms as well. And this is just a boundary term that's derived from all of these classes, from the Chern's classes and the Poincaré classes. There's also something I don't even think did I add it? I think I forgot it, but there's also something called the Euler class. We can't forget about that. Which this is the topological invariant integrated in the Gauss-Bonnet theorem. Okay. So in the Gauss-Bonnet theorem, this is the Euler class, okay? Yeah, I didn't forget it. It's right there. But yeah, this comes from, so for SO4 gravity, the Poincaré class would be this. And so yeah, there's just different ways to, and again, it would be the trace of the curvature with wedged with itself over 8 pi squared. All right. So yeah, these are essentially what allows us to define topological charge. And physics at high energy is really dominated by local curvature, by the curvature two forms. And physics at low energy or large scales is dominated by these topological integers, if that makes sense. Okay. Let's look at gravity, or the Levi-Civita connection. Gravity is a special case, because we want to know, right? Like, where does gravity fit in? Why is gravity such a geometric theory? Or why was the instance of using geometry to describe forces really used in gravity first? How is this a justification for Einstein's theory of general relativity? Well, it turns out that gravity is a unique internal space, and it's the same. The internal space is the same as the external space for gravity, because the bundle is what we call the frame bundle, and again, it's the set of all coordinate grids at every point. So, a theorem that we have is that given a Riemannian metric, there exists a unique connection on the oriented orthonormal frame bundle, where if we have SO, the special orthogonal, acting on the manifold, mapping to the manifold such that it's torsion free, and the parallelograms like close, and that it's also metric compatible. That means it preserves lengths and angles. What happens is the curvature of this connection on the Riemannian the curvature on the connection is the Riemannian curvature tensor. And what that gives us is that Einstein's equation is simply relating this geometric curvature to the energy density of the universe. Okay? And so the causal formula, again, gives us that for vector fields, if we take, 2g of the connection, to ensure that it's torsion free, we can get this long kind of law for vector fields, and the Christoffel symbols then would generate the local coefficients of this connection that are used in general relativity. And so this is essentially what you'll be taught in any general relativity class. Had to go through, and I remember asking my professor, where does this come from? Why do we use this? Why does the metric, or why does the Levi-Civita connection, so we talked about the Levi-Civita connection, but like, why does this? What does this have to do with anything? And a little did I know that you have to have all of this background to really fully appreciate the special case of gravity for its internal space being the same as the external space, due to the bundle, or due to the frame bundle geometry. Okay, and if we look at a sphere, also, the standard metric on the sphere would be ds squared is equal to d theta squared times d sine squared d phi. Right, this would give us the longitude and latitude, and the Christoffel symbols for the standard metric would just be cotangent and negative sine and cosine times cosine, and all the other Christoffel symbols are 0. The Riemannian tensor component would then be sine squared. This would give us the geodesic curvature for a sphere. All right, so, and that would make sense, right? That the Riemann curvature tensor component for this would be sine squared. So let's look at a unified table of all the classical forces. Again, this is the standard model of physics in one geometric table. So to fully appreciate this, you can see that, for the geometry, or the bundle, we choose, for gravity, we choose the orthochronous. Essentially, this is what this is called, the orthochronous special orthogonal group of matrices from 1, 3, and essentially it's just a Lorentz frame bundle, and it gives us the local gauge field of a tetrad plus a spin connection, and the curvature or the field strength is Riemannian, and you can think of this as like tidal forces or space-time curvature. That's kind of what the gravitational interaction is in kind of this metaphysical sense. If it has all of these qualities, then it's gravity. Okay. It has this structure group. It uses a Lorentz frame bundle, and it obeys all of these things, right? And it comes from this curvature or field strength. The properties of the curvature, and the curvature itself is the Riemannian curvature tensor. Okay, it's defined uniquely by the Riemannian curvature tensor. In E&M, we're typically looking at a U1 line bundle, and the principal bundle becomes a complex line bundle. The local gauge field is a photon, and it's defined, or its curvature 2 form is defined by just the exterior derivative of that. And again, it's abelian, so because it's an abelian curvature 2 form, we only need to take the exterior derivative of the potential 1 form, okay, or connection 1 form. So we would then have the electric and magnetic fields coming from this. All right, to physically interpret that, an electromagnetic interaction usually looks like this. If we look at the weak structure group, so what this looks like is a left-handed SU2 bundle, and the SU2 bundle then gives us W and Z bosons, and also just weak bosons in general that obey a non-abelian curvature form. So the curvature 2 form would, the connection 1 form has a wedge product that is non-zero, and they are non-abelian, and so this again gives us the W and Z boson fields, okay, for a nuclear decay and weak interaction and stuff, whatever. These happen to be unified, but I'll save that for another. It's nice to learn these first as separate kind of fields. Then we also have a strong force, which is given by the color bundle. And what a color bundle tells us, again, is that we get another non-abelian group, and the gluons hold the nuclei together, and it's generated by these kind of more complicated symmetries that corresponds to color, but color is very misleading, thinking about it in such a way. So the symmetry groups in general, but yeah. Anyways, really, we've geometrized force. All right, force is geometrized. It's and this is the standard model of physics. It is purely a geometric kind of way of thinking about everything. It's no longer a vector that's pushing things around. It's really the curvature of the fiber bundle that is describing the internal symmetries of the universe. Okay? But we have a problem, which is that we have described the stage or space itself and the forces, curvature, but we haven't really described the actors themselves, right? Like, so what's an electron? We haven't really answered that question. Or what's a quark, right? In classical physics, they're points, right? But in this framework, we need something geometric to describe electrons, quarks, and we need a way to think about particles instead of like classical physics. But we need quantum mechanical. We need to describe quantum mechanics, which shows that there's really no such thing as a particle or a point, right? Quantum mechanics culminates in the fact that everything's actually a representation, or we need to have a periodic table of physics, like in terms of mass, spin, and antimatter. We need to find this from the symmetries of space-time itself, okay? So what this leads us to is quantum mechanics. So in classical physics, a point particle is just some point with mass, right? In introductory quantum mechanics, a particle is a wave function, right, or state. The state is a generalization of a wave function. Both of these definitions are wrong. They rely on position, which is not a fundamental invariant of relativistic spacetime. And in this section, we're going to define a particle not by what it looks like, but how it transforms. So the definition of a particle now is going to be an irreducible unitary representation of the symmetry group of the universe, the Poincaré group. So what we'll get is that mass is not a weight, it's the eigenvalue of the translation Casimir operator p squared. Spin is not a rotation, it's the eigenvalue of the Pauli-Lubansky Casimir operator. And antimatter is actually not a separate substance from matter itself. It's just a mathematical necessity required to make these representations consistent with causality. From this perspective, pioneered by Wigner in 1939, this actually explains why electrons must satisfy the direct equation, and photons must satisfy the Maxwell's equations. And these equations are merely projections of the same representation onto spacetime. All right. If we look at the Poincaré group, the symmetry of spacetime is encoded at the stage of special relativity, which is via Minkowski spacetime. And the symmetry group is the Poincaré group, which is the irreducible special orthogonal 1,3 group. And it consists of two parts. It is also orthochronous, okay? Which basically means that there are translations that are defined by moving through space and time. And there's also Lorentz transformations, which are rotations and boosts. The Poincaré group here is the product, is the semi-direct product of the real numbers in 4 dimensions and the special orthogonal group in 1,3, all right, with orthochronous, okay? So the Lie algebra of this group contains 2 special operators that must commute with everything else, and they are called the Casimir operators. And by Scher's lemma, essentially by Scher's lemma, we have that any irreducible representation, which is again a single particle, for any of them, these operators must be constant numbers. So p squared again is going to be just the contracting the vectors for this representation. Okay, for the this invariant will be labeled as the mass squared, right? The mass squared is the invariant itself, and then the spin squared is going to be w squared, which essentially is the Pauli. These are the Pauli-Lubansky vectors. Okay, and this invariant measures the intrinsic spin. Okay, or some intrinsic spin. All right, and it's actually a pseudovector. Okay, which a pseudovector just means that if you try to essentially the negative version of it, like if you were to have a vector and then like have the negative version of it, it's not like going to reverse any negative signs. Okay, and then of course this then gives us the Lorentz or the commutation relations again that must be satisfied for these particular operators, and where this eta sub mu is the specific Minkowski metric. Okay, so again, and these are Lorentz transformation matrices that encode rotation and boosts, right? And of course, in units of h bar and c to be equal to 1, again, this is the form momentum. It's a Hermitian matrix, and these are Lorentz boosts and rotations are also Hermitian. Okay, and we can look at a free particle at rest. The form momentum would look like this, and the Pauli-Lubansky pseudovector looks like 0 and j, where j are the angular momentum operators. right? And this entirely encodes our idea of a particle, right? It's just the irreducible representations, and it's a particle. A particle is always uniquely defined by two numbers, m and or basically the mass and the spin squared. All right, the intrinsic spin of the system. So that's a particle. Okay, a particle is mass and spin. Now, Wigner's classification gives us the periodic table of physics, basically, because we can list every possible particle that's allowed by the laws of relativity, given this definition of a Newton definition of a particle. So if we say a massive particle, where we have that the mass squared is greater than 0, it's just massive. Then if a particle is massive or has mass, we can go to the rest frame where the momentum gives us some mass and no angular momentum or whatever, or no velocity. Okay, and again, this is just the time component of the four momentum. The symmetries that leave a particle at rest are just the spatial rotations, the special orthogonal matrices in 3 dimensions. Okay, so just SO3, and we can we can say that those massive particles are classified by representations of SO3. So if we have spin equals 0, this is the Higgs boson. So it's a scalar particle. If we have J equals 1/2, where the intrinsic spin is 1/2, then guess what? That's the electron or the quark. And these are described by mathematical objects called Dirac spinors. They have 4 components. But that's just kind of what they are. And quarks as well have spin 1/2. Spin 1 particles are the W and Z bosons, and they're essentially massive vectors. So they're vectors with mass, and they have 3 polarizations in rest frame, and they're boosted. If you boost them, you'll get a Praca field, which basically gives you spin and mass together. And then where J is equal to 3/2, we associate these with gravitinos, or Roida-Schringer representations of the SO3. And essentially, these are all the cases that you can give for representation, or not really every single case, but these are the most important ones. Okay, so the spin can be either 0, 1/2, 1, 3/2, etc. All right, and this is for standard momentum. For massless particles, where m squared is equal to 0, if a particle is massless, like a photon, it has no rest frame, and it moves at c. It moves at the speed of light. It is essentially just a characteristic of an invariant quantity of the vacuum. All right, the speed of light itself, c, is not really the speed of light, because the speed of light actually travels within mediums. And so what you want to do is actually show what you want to encode the invariance of this two-way speed of light that we measure in the vacuum, and that's essentially what that Lorentz speed is. Okay, c is not really the speed of light. All right, that's really important to understand. Speed, or c, is a Lorentz invariant, and it should be called the Lorentz speed. Okay, and what this does, it just tells you the propagation of interaction for particles. So if m is equal to 0, and essentially if a particle is massless, like a photon, it has no rest frame again, and the symmetries preserve a light beam. And a light beam are not rotations; they form the Euclidean group of a plane. So they're irreducible special representations of either ISO2. Okay, and because they're ISO2, they are the semi-direct product of the real numbers composed with the special orthogonal matrices, and they call this a little group, right? And they span, again, the Euclidean group of the plane. This changes the structure entirely, because we don't have spin, we have helicity. So helicity then is essentially a finite dimensional representation that requires the translation of ISO2 to be 0, and we're left with the special orthogonal to rotations 2 around the momentum axis. And again, by getting helicity, defining helicity with lambda being plus or minus j, or the square of the spin squared, this is appearing for two states of the magnitude of lambda is greater than or equal to 1. So for a photon, there can exist two polarizations. And note, a massive vector has 3, a massless vector has 2. All right? So it only has, there's only 2 ways to polarize it, and mass kills a degree of freedom. So if there's no mass, if the bosons have no mass, or if the massless particles don't have anything, then it kills a degree of freedom. And remember, we're talking about particles in general here, just in a mathematical sense. We're not specifically, of course, it's synonymous with physics, but this is a geometry of physics, essentially. All right? Now, a vector field with a Lorentz gauge, which says that if we take the four derivative of the potential to be equal to 0, and its equation of motion gives us the D'Alembert operator on the vector field is equal to 0, and we also have the Maxwell vacuum being satisfied, where the four derivative on the strength energy tensor or the curvature 2 form, whatever, this is in coordinates. We're restricting ourselves to coordinates here. Because we fixed ourselves to a gauge, there are 2 transverse polarizations. All right? And this describes a photon. Now, if we want to describe a graviton, which gives us 2 tensor polarizations, we get a symmetric tensor, which just means if I were to reverse the indices, they are, and essentially they are also trace-free and linearized with the Dodonder gauge, which essentially, if we take the four derivative of the tensor itself, that should be equal to 0, and if we take the D'Alembert again of the tensor should be equal to 0. So again, we get continuous spin representations, or finite dimensional continuous spin representations are unphysical. All right. So sorry, infinite dimensional. So yeah. So there's only a couple spin representations, or there's only a finite number of spin representations that are physical. Okay, it must be finite dimensional, so integers or half integers or whatever. Okay. Now, crucially, a massless vector particle has only 2 degrees of freedom, or just transverse polarizations, and this is even for the graviton. So the longitudinal mode is unphysical, and that's why gauge invariance is required for massless fields to kill that ghost mode of those longitudinal modes. Okay, so there's only transverse polarizations for massless vector particles. That is dictated by the irreducible representations. Let's look at a one particle Hilbert space. All right, and what we can look at for the one particle Hilbert space is, if we have, again, a Hilbert space from the continuum analysis video that we did, is the space of square integral functions on the mass shell. So the hyperbola is defined by p squared is equal to m squared. For massive spin J, okay, we would say that the one particle Hilbert space would be the tensor product between L2, okay, the space of Lebesgue integrable functions, or essentially the Banach space where p is equal to 2, on the real numbers in 3 dimensions, as well as with D3, the momentum density in the three dimensions being normalized by the energy with respect to this energy, and this will be a tensor product. Okay, we're taking the interaction between the vector spaces in the physical space, as well as with the spin structure, and again, this gives us the space of square integrable functions that obey this particular spin structure. And to transform, or the states will transform via Wigner rotations. All right. But if we want to do the Poincaré action on the induced representation, this is essentially how we would encode this, where W of lambda comma B is the Wigner rotation. So we would do a little group element taking lambda P naught to P naught, okay? And that's what this would look like. So again, we have this function, this wave function that's being acted on in terms of from these unitary transformations in terms of the induced representation from the Poincaré action, all right? And when we do a spin mix, this depends on the momentum, and this is called the Thomas precession, okay? And the Thomas precession specifically allows us to, or it's a phenomena that takes essentially like like if you've seen a precession of a top, right? Like precessing around some like tracing a circle or whatever. Well, this is like just kind of a irreducible representation theory of this, where we have particles that have mass and spin, okay? And we can encode this specifically with the Wigner rotation. Now, if we look at a theorem, it's called Newton-Wigner. There is no covariant position operator for a relativistic particle. All right? This means that you cannot localize a particle faster than the Compton wavelength, and if you try to squeeze a photon into a box smaller than its wavelength, you will create a pair production. So the single particle picture breaks down, and the Newton-Wigner position operator exists, but it's non-covariant. So that means that for some spin zero system, if we construct a Hilbert space for one particle, the wave functions then a wave function is a function of a position. If we change it to another function as a function of momentum, and we want to map it to position, we would then have to integrate, and it's basically like a Fourier transformation, okay? And there's no sharp localization of this because of the rules of the Hilbert space, okay? Now, if we want to look at field representations, what we'll have to do is, if we want to get away from this abstract group theory to like wave equations, like the Dirac equation, we really need to ask what kind of field can carry this representation, right? To realize the irreducibles locally on Minkowski space, so let's say we have a spin zero or scalar field, okay, or just as a function of x. The constraint is that the momentum squared should be equal to the mass squared, and so we get the Klein-Gordon equation for a spin 1 scalar field. For a spin 1/2 spinor field, we need a representation of the Lorentz group, and this is called the special linear group on the complex line, or on the complex plane, and the direct product between 1/2 tensors here. This representation allows for a mass term, and the m comma 1/2 representation is irreducible representation. Is two-dimensional, and the full direct spinor coordinates would then just be the direct sum of these two tensors with opposite parity or charge conjugacy. So then this equation could give us the Dirac equation. All right. And then, of course, to derive this, the Lorentz group has spinor representations of SL2, C, and these irreducible representations are two-dimensional Weyl spinors. So, to get a massive particle with parity, combine left and right-handed spinors, and the Dirac equation couples them with a mass term. So that's how you would essentially get this and solve for that wave equation for a spinor field, okay? And then, so then, really, what's happening here? Oh, and also for a spin 1 field, for a vector field, you would get the massive Praca equation with the Dillon-Bertian operator plus the mass, again, acting on the vector field, and then that should equal 0 again, with the constraint that the Fourier derivative of this Praca field is equal to 0. So this gives us 3 degrees of freedom. So that's the spin 1 wave equation. And massless, so if it is massless, then from the Praca field, the special case of the Praca field gives us the Maxwell's equations. that assumed gauge invariance is required to kill those the non-physical polarizations from the mass. Okay, and so again, to get rid of that 1 degree of freedom. So that's how we would dictate gauge invariance. For a spin 2 field, where we have that, it's a tensor field, basically. If we want to solve a tensor field, massless helicity is plus or minus 2, so the symmetric tensors should be equal to each other, and it should also be trace-free and linearized in the Donder gauge. So again, if we take the Fourier gradient of the tensor, it should also, that should be equal to 0, and the D'Alembertian the D'Alembertian of the tensor should be 0 as well. All right, so that's how we would solve a spin 2 tensor field. So that's how you do this with field representations and the Bargmann-Wigner equations, right? So that's great. But again, how do we think about this? This means that the Klein-Gordon equation, the Klein-Gordon equation realizes this locally on Minkowski space, and again, we needed the spinor representation of the Lorentz group, but we also need parity, again, symmetry between the left and the right spinors, and this requires fusing 2 Weyl spinors from the direct sum. And so that equation couples them. Again, Dirac didn't really invent this equation. It is the unique differential equation that projects a bispinor field onto the irreducible representation of m, 1/2. Okay, so that's kind of why it works the way that it works. Okay, so you didn't really invent it. Now, the spin statistics theorem tells us, why do electrons repel? So Fermi-Dirac statistics. So while photons clump together, Bose-Einstein statistics, these are two contradictory type things, because experimentally, this seems like an accident, right? Like electrons repel, but photons clump together. It's kind of weird, right? Well, we'll get the rigorous, it's a rigorous theorem of quantum field theory. So there's a theorem from Pauli in 1940 and some other people, that in any local Poincaré covariant theory with positive energy, okay, particles with integer spin must commute, okay, and they're bosons. Particles with half integer spin must anti-commute, and they're called fermions. And if you try to make a scalar field a spin 0 anti-commute, the energy of the vacuum becomes unbounded from below, and so the universe just essentially explodes. All right, so proof by reductio ad absurdum. If the universe explodes, right, that's not great. So if you try to make an electron commute, causality breaks down. And so consistency with relativity forces the statistical nature of matter. And so, for example, we can look at a pion, which is a spin 0 particle. It commutes. And an electron, a 1/2 particle, anti-commutes. And then this implies the Pauli exclusion principle. Okay? Let's also look at the Unruh effect. So what is a particle? All right? Now that we have particles themselves, we have how to describe particles, but what the hell is a particle? Well, it turns out that we just we actually have a disturbing crack in the definition of a particle, because we've defined a particle using the Poincaré group. But the Poincaré group is the symmetry of flat spacetime. Okay? What if space is curved? All right? Or what if an observer is accelerating? This is called the Unruh effect. It's very strange, which is that an observer moving at a constant velocity sees a vacuum. 0 particles, right? If you're going to 0 constant velocity, you're fine. But if you're an observer that's accelerating, or a Rindler observer, that is thought the vacuum sees a thermal bath of particles. Okay, and that essentially that with the temperature is equal to the acceleration of your frame divided by 2 pi. So again, to an accelerating observer, the vacuum will look like a hot gas. All right, so it depends if you're accelerating or not, whether you're looking at a vacuum, what your opinion of the vacuum is. All right, depending on your observer and if you're accelerating in your frame. So this means that a particle itself, this is very consequential because a particle itself is not objective reality. Particles are what we say observer dependent. So this leads directly to Hawking radiation, where the curvature of a black hole creates a thermal bath for the static observer. And this essentially, by the equivalence principle, gravity creates a similar bath, thermal bath for a black hole. So a static observer outside the Schwarzschild black hole of mass m sees a Minkowski-like vacuum past null infinity as thermal at T is equal to 1 over h pi gm. And this is essentially the temperature of the horizon of a black hole. And we can calculate exactly what that surface is, or the temperature of that surface is. And keep in mind, this isn't necessarily the temperature that's coming out of the black hole per se, but it's the temperature that's encoded on the surface of that black hole, because the vacuum, or in other words, that point at infinity, or the Minkowski-like vacuum at past null infinity, is this because of the accelerated frame. All right. So again, both arise from something called the Bogoliubov. Okay, I can't even say it. Bogoliubov transformation between inertial Minkowski modes and accelerated Rindler modes and curved Kruxel modes. Okay, to derive this Hawking radiation, and this transformation has a non-trivial beta coefficients from the statistical from the from the partition functions, and this corresponds to particle creation on the horizon. All right, so that's where that radiation is coming from. Particles depend on your observational frame. So uniformly accelerated detectors as well in Minkowski space links with the thermal spectrum as well. Okay, so in conclusion, we've defined matter. Matter is not made of stuff, okay? It's made of representations, and then remember, representations are just symmetries which create space. Mass and spin are just labels, okay? And so particles themselves, again, what is a particle? It depends on your frame. If you're accelerating, then the particle really is not a meaningful thing, okay? It changes based off of your frame. So that's great. Mass and spin, again, define particles in whatever frame you're in that's not accelerating. And equations of motion are projectors. Statistics, the Fermi direct statistics are a consequence of just geometry itself, okay? And again, this explains the commutation, the space-like separation, the integer and half-integer spins, their commutivity and their anti-commutivity for fermions and bosons. Okay, but we have a problem. Houston, we have a problem. We have identified particles as free entities, right? But in the real world, particles, what do? They interact, they scatter, like billiard balls or waves, or interfere. And, when we try to calculate these interactions, we hit things called in our calculations, we hit infinities. All right, masses become infinite, charges become infinite. We get black holes and tears and everything in the universe, and when we calculate stuff. So to fix this, we have to accept that the laws of physics must change depending on how close you look to the system. Right? So if I'm looking at an electron and I'm really, really close to an electron, the laws of physics are going to be really different versus like me being like 50,000 light years away from the same electron. All right. So basically, this is going to allow us to describe something called statistical field theory and renormalization groups. All right, so this is where it gets really cool. This is where physics gets really, really interesting. Kind of, I think this is more of the more open-ended side of physics is statistical field theory, because we define a particle again as an irreducible representation of the Poincaré group. This gives us a clean kinematic picture of matter. But in the real world, particles interact, and when we try to calculate these interactions using quantum field theory, we encounter the problem, which is infinity. So the mass will become infinite. Charge becomes infinite, and for a long time physicists thought this was a mistake in the math, but today we know that it is a perfect signal. It tells us that the constants of nature are not constant at all. Okay, mass, charge, and coupling, they're not constant. They depend on the resolution at which you are actually looking at the system. This is actually a physical thing. So this section here, we're going to cover quantum field theory with statistical mechanics. And we're going to see that a vacuum fluctuation is mathematically identically identical to a thermal fluctuation. And we will introduce the renormalization group. This is kind of a meta theory that describes how physics flows as you zoom out from the microscopic to the macroscopic. So let's look at a Euclidean path integral and statistical mechanics. This is the deepest link in modern physics because it's the mathematical identity between a quantum particle moving in type T and a statistical system at thermal equilibrium at temperature T. And this is what we call a Wick rotation. We can perform an analytic continuation of time to the imaginary axis. And what this does is transform the Minkowski metric here to Euclidean space with a metric 1, 1, 1, 1. All right. So it's just a matrix with this diagonal, and that's the matrix. That's the metric. So it's 40 Euclidean space. We can turn Minkowski metric to 40 Euclidean metric, and it's all fun and games. The partition function map is an oscillatory path integral of quantum mechanics, and it transforms into the exponential partition function of statistical mechanics. All right, and so the action S sub E is the energy functional of a statistical system. Okay, so we just transform this path integral here, where we integrate over the measure for a probability amplitude. We then turn that into, via this Wick rotation, we just turn that into a Boltzmann weight of a particular partition function. All right. And so by doing the Wick rotation, we integrate over the Euclidean metric, and they are equivalent. So the action is now the energy functional of a statistical system. And why is this important? Because if we look at... Oh, well, hold on. Before we go on to this, temperature. What is temperature? In Euclidean quantum field theory, temperature corresponds to compactifying the imaginary time direction on a circle of circumference. Beta is equal to 1 temperature, 1 over temperature, right? So for a finite temperature, we want to compactify the imaginary time direction between the interval from 0 to 1 over the temperature with periodic boundary conditions for bosons and anti-periodic for fermions. All right, and what that will do is then give us a clean translation from Lorentzian quantum mechanics for the path integral of Lorentzian quantum mechanics to Euclidean statistical mechanics. All right, so there's kind of a correspondence between Euclidean space and Lorentzian space if we define temperature in such a way. Now, if we want to look for a free scalar field, the Minkowski action looks like the integral over the density over a 4-dimensional hypervolume density for 1/2 m squared over the scalar potential and the kinetic energy. All right. Well, guess what? The Euclidean action, after rotating it or performing the Wick rotation, allows us to then get the exact energy functional for a continuous elastic sheet. So a quantum field in 4 dimensions is identical to a classical statistical system in 4 dimensions. Okay? And if we look at the Ising model, if we consider a lattice of spins, say sigma sub I is plus or minus 1, interacting with neighbors, the statistical system on a lattice with spins 1/2, given that, we can construct a Hamiltonian such that we'll get the negative of the spin summing over the indices of those lattice spins minus some h of the summing over all of the spins. And when we look at this in the continuum limit, the spin field becomes a scalar field, and the action becomes something called the Landau-Ginzburg functional, or phi to the 4 theory. All right, and so this also gives us the statistical or the Euclidean action. Okay, so there's another way. We don't just have to do a Wick rotation, but we can also look at the Ising model as well for Landau-Ginzburg functionals. Okay, if we look at the XY model, let's look at spins on a circle. This corresponds to orthogonal to an O2 scalar field with a global symmetry, and at low temperature, this implies that we can have a massive phase and a high temperature, and it becomes a disordered field. So we can construct then as well correlation functions. So this is another way to encode quantum field theory into statistical mechanics, or in other words, we can construct Euclidean actions with Minkowski actions and get them equivalent if we correspond or if we correlate them, okay, with global symmetry. So another thing is that we have infinities, and renormalization is not about sweeping infinities under the rug, right? When we integrate these things, they can blow up, right? So we need to do something called coarse graining. And you need to imagine a grid of spins or magnets, right? Imagine like a grid of just like a bunch of magnets. And if you look closely, you'll see individual atoms like flipping. But if you blur your vision, the spins in a 2x2 block, if you average them into a single effective spin, this transformation will change the Hamiltonian. All right? And in other words, it changes the energy. So a coupling constant and interaction strength shifts. If you repeat this process, zooming out, averaging, and rescaling, you generate a flow in the space of all possible theories, if that makes sense. So what category theory is to mathematics, right? Metamathematics or whatever. The renormalization group is that to physics, because it's like, again, if you look at the precise Hamiltonian system, but then you blur it and then average it, that's a different energy. And you just keep reiterating this over different scales, and that gives you a flow. Remember, in the space of possible theories. So, the coupling constant, well, okay, so let's talk about the renormalization group step. So if we want to approach this in a Wilson approach or Wilsonian approach, we first do is the cutoff. We assume that the theory is defined up to some high momentum scale. So we'll say lambda is just the pixel size essentially of the universe that we are concerned with, or that the theory is concerned with. We're going to integrate out. So we'll perform the path integral over the high momentum shell. So we'll do the pixel size divided by some b, some parameter b, less than or equal to the magnitude of some k, which is less than the pixel size of the universe. Okay, and then we'll rescale. So scale the lengths and the momenta accordingly, linearly, to restore that original cutoff. And then the effective action is the remaining low momentum modes obey a new action with modified couplings, we'll say G of mu. This renormalization group transformation consists of integrating out high momentum modes, okay, and rescaling momenta to restore this cutoff, all right? And that effective action at a coarser scale acquires new couplings. So we essentially are creating some transformation from this original coupling we then have to correct it for particular loop integrals as we zoom out, okay? And this gives us a coarser scale. All right, so we'll then define something, again, repeating the process, zooming out, averaging, rescaling. You generate a flow, and this is called the renormalization group flow. And the renormalization group flow is just the rate of change of the coupling constant as we change the energy scale, mu, where mu is the sliding scale, and it's a differential equation. Okay? So a beta function, or some beta is always a function of the coupling, all right? We're trying to solve this. So a beta function tells you how the coupling constant G changes as you move the energy scale, mu. And so for a one-loop beta function, for a scalar in 5-4 theories in d dimensions, all right, beta of lambda is equal to 3 lambda squared over 16 pi squared in 4 dimensions, okay, and d equals 4. And this is marginal and irrelevant in d is less than 4, okay? So this would describe our one-loop beta function. So for some given coupling, all right? And let's look at the first case of phi to the 4th theory screening. So in electromagnetism, the vacuum is filled with virtual electron-positron pairs. And they act like dipoles. So they're going to shield the charge, right? Because, you know, electron and protons like cancel out the charge, right? So if you zoom in, though, at high energy, you will penetrate this kind of like shield of charge, and the charge will look bigger. If you zoom out, low energy, the charges look smaller. So that means that the beta function is positive. The theory is strongly coupled at high energies, which is called a Landau pole, and weakly coupled at low energies. So in 4 minus epsilon dimensions, we can then have, in general, the beta function to give us this renormalization group flow, okay? At a Gaussian fixed point, this would be said to be U ultraviolet attractive for E is greater than 0, and the Wilson-Fisher fixed point gives us the infrared attractive part of the theory. So again, as mu increases in the ultraviolet, lambda increases. As the energy decreases in the infrared, lambda flows to 0, so the interaction washes out at large distances, and this is called the Gaussian fixed point. All right. For quantum chromodynamics or asymptotic freedom, the strong force, which is a non-abelian gauge theory, gluons themselves must carry charge, so they don't shield, they anti-shield or smear out the charge, and this will lead to a negative beta function. Okay, so it's the asymptotic freedom is opposite of the quantum electrodynamics of renormalization. So again, this negative beta function for a pure SU in, so just any special unitary with in flavors of quarks, all right. The one loop renormalization flow is equal to negative 11 in over 3. times coupling constant to the cubed over 16 pi squared. And for NF flavors, we can have this closed form, which says for n is equal to 3, right? For 3 essentially, the number of flavors, can is less than or equal to 16. These are asymptotically free. And for the number of flavors to be equal to 6, so this is the real case of quantum chromodynamics, it's asymptotically free. So the result is for real quantum chromodynamics, n is equal to 3 and nf is equal to the number of flavors 6. The coefficient is negative. The implication from this tells us that as the coupling constant in the ultraviolet tends to 0, quarks behave as free particles, or they have asymptotic freedom. But in the infrared, or low energy limit, the coupling constant goes to infinity. So the force becomes infinitely strong, and this causes confinement. This means that quarks are permanently locked inside of the photons, mathematically, because of the renormalization group, in the space of all the possible theories that could be coarse-grained from it. Okay, so that's great. And there's also something called universality in critical exponents. So the renormalization group flow explains why the universe looks simple at a macroscopic scale. Because most interaction terms you write down, like let's say 5 to the 6, 5 to the 8, gradient of 5 to the 4, they're irrelevant. Because as you zoom out, their coefficients flow rapidly to 0. So only a few terms like mass and 5 to the 4 survive. And these are what we say are relevant. All right, so there's irrelevant and irrelevant operators. And this leads to the idea of universality. Okay, so again, near a fixed point for some G star, some coupling constant, if you linearize the flow, Y would be the eigenvalues of the stability matrix. Okay, and this is the basic methodology that we do. We take the variation of this to be approximately equal to some of some group transformation, okay, for some Y of the stability matrix. And for relevant operators, let's say Y is, Y sub I is greater than 0. If it grows under the renormalization group if it grows toward the infrared, then it's irrelevant if Y is less than 0, and it's marginal if Y is equal to 0. So the renormalization group will end at fixed points for scale invariant theories, and hence this will give us the Gaussian fixed point for a free field theory, or Wilson-Fixture fixed points for non-trivial interacting theory describing phase transitions. And so in general, this leads to universality. A magnet is made of iron, and a fluid is made of water, and together they're totally microscopically different, right? Because the iron, is magnetized, has magnetized domains, and the fluid of water, they're it's just water, it's like a bunch of polarized, H2O. Whatever. It's like more complicated than just iron, right? But near a actually technically iron is kind of like crystal or solid state, but let's not get into that. The whole point is near a phase transition, they actually will behave identically. Okay, they have the same critical exponents, and the reason why is because they both flow to the same fixed point of the renormalization group. So nature will forget the macroscopic details once they have been averaged out. Okay, and so, for example, if you look at a 2D Ising model, the exact solution is a critical temperature with some order parameter that scales with beta to be equal to 1 over 8. If you look at a conformal field theory description, a minimal model with C is equal C is equal to 1/2 with primary fields epsilon, with that depend on some energy and delta 1, or a spin or sigma with some spin and delta is equal to 1/8. Okay, that will give us a conformal field theory, and then we can get an exact solution as well for a 2D Ising model. For 3D Ising models, flows towards the Wilson-Fixture fixed point with some orthogonal, some O1 symmetry, okay, we can get numerical exponents that look like this, and those are exact. And you can also look at ON, a vector model in 3D. And for n is equal to infinity, you get an exact spherical model for finite n universality classes. So there's a Heisenberg universality class with n is equal to 3, and with some xy class for n is equal to 2. All right. And so these are exactly solvable Ising classes, or Ising classes for the universality, for different microscopic systems that behave the exact same as so the physics are the exact same at different infrared or even ultraviolet points as well. Okay, so again, the Ising model share the same exponents because they both belong to the universality class of a scalar field with Z integer mod 2 symmetry. Now let's get into spontaneous symmetry breaking, or SSB. So sometimes the vacuum state does not respect the symmetry of the laws. So think about a pencil that is balanced on its tip, okay? The laws of gravity are rotationally symmetric, right? But if a pencil falls, it's going to pick a direction, right? The symmetry itself is broken. So what the Goldstone theorem tells us is if a continuous symmetry is broken, or I guess is said to be spontaneously broken, there must be a massive particle called a Goldstone boson. And this is the excitation that corresponds to rolling the pencil around the bottom of the valley. It costs 0 energy. Okay, so in a superconductor, right, the photon would gain mass, and this is called the Mersner effect. And in the standard model, the W and Z bosons gain mass by eating the Goldstone bosons of the Higgs field. All right, so essentially what this does, though, is if you break this global symmetry to a subgroup in the vacuum, there's one massless boson for each broken generator. So the dimension of the global symmetry group subtracted from the dimension of the subgroup gives us that the one massless boson, essentially. And so the dispersion, let's call it omega, would be some c times magnitude of k, which is gapless. And that essentially means that the potential will look like a Mexican hat. So what that looks like is the vacuum will sit in a valley, and moving along the valley costs 0 energy. And that's kind of the massless model, but moving up the valley costs energy, and that will give it a massive mode and generate the mass for the electroweak interaction, okay? Or generate mass of just matter in general for particles. So again, you can look at the Heisenberg ferromagnet. So with the global symmetry group of SO3 and the subgroup for magnetization direction is a SO2. So if we have 2 broken generators, you'll get 2 Goldstone modes with spin waves and things called magnons. Okay, these are just particles that are results of the difference in the dimension between the subgroups. Okay, and the representations of that. There's also pion effective theory. So you can look at chiral symmetry for the SU2 left-handed part versus the SU2 right-handed part, and this could break into SU2 V, where the pions then are Goldstone bosons. And quantum chromodynamics at low energies gives a chiral Lagrangian with pions as Goldstone bosons of SU2 sub L and SU2 sub R to then map to some other SU2. All right. So it mixes the left-handed right-handedness and generates mass. There's also the superfluid, and this should be for helium-4. or just alpha particles. The global U1 phase symmetry will break, and you can have one Goldstone superfluid sound mode. Okay, so that's pretty cool. And if you look at the standard model, the left-handed SU2 cross the U1 can be broken to the electromagnetic U1 by the expectation value of that group not being 0. And so with 3 broken generators, you'll get 3 Goldstone bosons that are eaten by the W plus or minus boson and the Z boson. These are massive gauge bosons that are generated by the Higgs mechanism. So the photon will remain massless. And there's also, again, the confinement and mass gap. So in a non-abelian gauge theory like quantum chromodynamics, the coupling grows strong in the infrared. So field lines do not spread out like electric fields. They form things called flux tubes because they're kind of the inversion of the electromagnetic kind of behavior at the Gaussian fixed point and Wilson points. So what we do is in non-abelian gauge theories, without large charge matter, with strong coupling in the infrared, this will lead to something called confinement. So the Wilson loop criterion. So let's say if we consider a loop tracing the path of a quark anti-quark pair as the expectation value of that loop to be equal or to be distributed accordingly by just some exponent of that depends on the area and of some string tension, the area law will imply a linear potential that's just linear with respect to some string tension within that loop. All right, and the result is that it takes the infinite energy from 2 separate quarks, and this is called confinement. And to contrast with electromagnetism, the Wilson loop follows a perimeter law, so it implies a Coulomb potential that quarks, 1 over R law, which that quarks would be free. All right, so the Wilson loop criterion will tell you a lot about how the physics behaves and the idea of confinement and how mass gets generated in confinement. So for pure SU3 Yang-Mills, the asymptotic freedom implies that there's weak coupling at short distances that is strong at long, and so we'll get flux tube formations, and so then we get also the confinement of color charge. All right, so in a pure SU3 Yang-Mills theory. In a QCD with heavy quarks, you can see a quark-anti-quark potential rises linearly with large R, which implies that there's no free quarks or confinement, right? But the chiral symmetry breaking at low energies happens. Okay, so this is more of a question of where is the mass allowed to be generated, or where do we see confinement and mass gaps? Okay, because the field lines don't spread out like electric fields. We also can look at the Hooft-Polycon monopole in the Georgi Glashow model. Confinement of electric charge by the dual Meissner effect around magnetic monopoles is another kind of result as well from confinement and mass gaps. In effective theory, we can summarize basically the modern philosophy of physics, which is that every theory is an effective field theory. Okay, we don't need to know the ultimate theory of everything to calculate the path of a baseball, right? The high energy physics, string theory, decouples from low energy physics or Newtonian gravity, and heavy particles can be integrated out, leaving behind small corrections to the coupling constants of the light particles. And so we essentially can then describe every layer. We can really just describe every layer by layer. So heavy fields, again, where the mass is much greater than the energy. This decouples from low energy physics up to corrections of order the energy over the mass. Heavy fields with mass decouple from low energy physics. Again, their only effect is to shift the coupling constants of the light fields to generate suppressed non-renormalizable operators that are suppressed by powers of 1 over m. And the low energy effective Lagrangian is the most general local operators that are consistent with symmetries ordered by dimension. So it's telling us essentially, we're doing a good job at doing physics in a particular domain. We just need to make sure that we're appropriately keeping track of like whether the physics here is effective or not, depending on the mass with respect to the energy scale. Okay. The Fermi theory of weak decay. Before we knew about the W boson, we described, which has an energy of 80 gigaelectron volts. We actually described beta decay using a 4 fermion contact interaction, with the Fermi constant just being a coupling divided by the mass, or the mass of the weak interaction, okay, or mass of the W boson. This is actually simply the low energy limit of the standard model, where we have integrated out the heavy W boson propagator. And so when we integrate out the W boson from the SU2L left-handed interaction with the unitary group, this leaves a 4 fermion interaction, which creates the effective constant of the Fermi constant. Okay, so this is the Fermi theory of weak decay, and so yeah, that's pretty important. Also, you can integrate out the top quark. So with the heavy top quark, which is much less than the other ones, it contributes to the dimension 6 operators, which looks like this, and 4 fermion operators modifying B to S in transitions for the Mendelssohn variables. Not super important, but again, it's effective physics. And also there's something called pion effective theory. So quantum chromodynamics at low energies. So if we have a chiral Lagrangian with pions, which are spin zero particles, as Goldstone bosons, so they have mass, right? And they essentially describe the product, or the group product between the left-handed and right-handed SU2s to map to some U1. Again, that gives you pion effective theory. So we can use effective field theories, depending on low energy and high energy things, because of the Apple-Carson theorem, okay, in 1975. So this allows us to essentially just we've really tamed the infinities that we had a problem with, right? Because we can define physics layer by layer. We replace really the static constants, right, of nature, those constants that we thought were constant, with a dynamic flow. We also found that the vacuum is a statistical medium. So we explain mass as symmetry breaking and confinement as renormalization group flow. There's one problem. We built, classical mechanics, right? Symplectic classical mechanics. And we also built quantum mechanics with Hilbert spaces, and, how to, integrate over particles and irreducible representations and all this stuff. But we haven't really explained how to get from one to another, right? Is there a map between symplectic spaces and Hilbert spaces? That's kind of the next question, right? Or even if there's a map that's similar to like the Wilson, or sorry, not the Wilson loops, the Wick rotations between, the path integral and the partition functions and Euclidean action versus the Minkowski action. Is there a map, right, between classical mechanics and quantum mechanics geometrically? And so this will lead us to, again, we haven't really explained how to get from one to another. And is there a rigorous map, or is quantization just kind of like a whatever, like an art or something? It's just mass and spin and whatever, it's some group structure. Well, it turns out that we can attempt to unify this, or create a map between them, by deriving Hilbert space directly from the topology of the space. All right. So what does this look like? We can arrive really at the final problem, because first we built classical mechanics, and it lives on a symplectic manifold, remember, omega, and the manifold, and then omega is within the manifold. And we also built quantum mechanics that lives on a Hilbert space. But for centuries, physicists use something called canonical quantization, and so they replace the Poisson brackets with commutators, which just basically means we just go from here to here. And usually like with 1 over h bar, or 1 over IH bar or something, times the commutator.
And that was kind of the recipe, right? It was just kind of an art. It wasn't like a geometric map or anything, and it failed for curved spaces because it depends on the coordinates. But geometric quantization is a rigorous attempt to derive the quantum Hilbert space directly from the geometry of the classical phase space. And what's important about that is we get a result that's shocking. We discover that you cannot always quantize a system. Quantization is not an algorithm, it's actually a cohomological obstruction. So when you can quantize, the number of quantum states is determined by the topology of the universe, or the Chern classes, right? So let's look at pre-quantization, which is a line bundle. And to make a wave function, and we mentioned this earlier for, the electromagnetic interaction, right? That depends on a complex line bundle. But to make a wave function, you need a place for it to live. And in classical mechanics, functions are scalars on phase space. In quantum mechanics, wave functions have a phase. A phase is a circle, U1, and therefore wave functions are not functions, okay? Wave functions are sections of what are called a Hermitian line bundle over phase space. Okay, so does such a bundle exist? The curvature of this bundle must match the symplectic form, where we have our curvature to form to be omega, right? But we know, again, that curvature is quantized. So the integral of curvature of a closed surface must be an integer 2 pi k. And this gives us then this, again, we get a cohomology class, an integer cohomology class. And this is what we call Dirac's quantization condition. The total magnetic flux must be an integer multiple of 2 pi, all right? And essentially, this is a subset of the real numbers. So, or the homology, okay, of the manifold. So, the prequantization, to make a wave function, we essentially need to impose an integrability condition. So again, it's only possible if the total symplectic volume, the magnetic flux, essentially the magnetic flux of the total symplectic volume is an integer. And again, that explains why electric charge is quantized. It explains why spin is quantized. And if geometry doesn't wrap around an integer number of times, the quantum Hilbert space does not exist. Okay? So again, if the condition holds, there exists a Hermitian line bundle from some base to the manifold with a connection nabla such that the curvature is the symplectic form. The pre-quantum Hilbert space then is a space of square integrable sections, which are Lebesgue integrable. And they are Hilbert spaces. Okay, and the pre-quantum operators for any classical observable f must construct an operator of basically the configuration space within that observable. Should the configuration space operator of that observable should give us minus I times the connection, okay, over that field plus the function. Okay. All right. And again, this is the Hermitian vector, the Hamiltonian vector field. This exactly reproduces the Poisson bracket algebra, all right, that we needed. So if we look at examples of phase space, R2, where the symplectic form again is a wedge product between dp and dq, the homology is trivial and quantization always works. But if we look at a sphere topology, where k, where the symplectic form is k sine theta d theta wedge d phi, the volume is 4 pi k. And so quantization only works if 2k is an integer, or if it has an integer spin. Okay, so this kind of checks out. This is really elegant. And if we look at polarization, this kind of makes it a little bit harder because the pre-quantum Hilbert space is too big, right? The space of sections of that manifold is way too big because it contains functions of position and momentum. And Heisenberg's uncertainty principle will forbid this. So a quantum state depends on Q or P and never both. So what we need to do is cut the variables in half, and this is called polarization. We need to choose a subspace of directions to kill. So if we take, for an integrable Lagrangian distribution, that's the subset of the tangent bundle, the complex manifold, we require that the physical states must be constant along these directions. All right? And so this allows us to define real polarization. And it's where the polarization, we basically just kill the momentum directions and the functions depend only on Q. And this gives us standard Schrodinger equations. And this is called the Schrodinger representation. We can also have complex polarization where we can kill something called the anti-holomorphic directions. And the functions must be holomorphic. This gives us the Bargmann-Fock representation, okay, of that particular connection, okay, acting on that wave function. Now, again, this would reveal what a quantum state really is geometrically by the polarization definition. The quantum state actually is, drumroll, a global holomorphic section of a line bundle. All right. Now let's look at the Atiyah-Singer index theorem. This is the $1 million question. How many states are there? If a phase space is compact, like a sphere, the Hilbert space should be finite dimensional. How do we count the number of holomorphic sections? Well, counting solutions to a differential equation is really hard analysis. But again, we haven't really talked about differential equations or anything. But the Atiyah-Singer index theorem actually turns it into a really easy topological problem. It says that the analytical index, the number of quantum states, is equal to the topological index, the integral of the characteristic classes. And so, for an example, we can look at the theorem, again, for a compact manifold, the analytical index, the number of solutions minus constraints equals the topological index, the integral of the characteristic classes. Okay, so again, the index of this map is equal to the dimension of the kernel minus the dimension of the co-kernel, which again is the integral. Is the integral of the characteristic classes. All right. So for particularly, did I work this out for a Hilbert space? Yeah. So if you look at the quantum Hall effect, consider an electron on a sphere with a magnetic monopole inside. Okay. The phase space is the sphere with magnetic flux K, and the line bundle L is over K, and the index formula is then given as such, where the dimension of the Hilbert space essentially will give us the dimension, because the index theorem will calculate the dimension for us topologically. And this is called the Riemann-Roch integral or index formula. And so basically the number of states is the lowest Landau level. So the physics or degeneracy is completely determined by the topology or the Chern number. All right. And that's essentially that allows us to determine the quantum Hall effect on a sphere. For topological quantum field theory, if we strip away the dynamics and we set the Hamiltonian then to 0, we will actually be left with pure topology. And this is Chern-Simons theory, all right? So this theory has no time evolution in a traditional sense, and it doesn't care about the shape of the manifold. It only cares about its knots and its links. So this Chern-Simons action, or Chern-Simons theory, I didn't put the Chern-Simons action in pure form, but it would essentially be S equals, I think, same thing here, and we're still integrating over the same manifold, but I think it would just be, Chern-Simons just did this with the connection one form wedged with the exterior derivative of that one form. But the extra terms come from Chern-Simons theory because this allows us to essentially show that a Hilbert space of this theory doesn't count particles. It doesn't care about the shape of the manifold. It counts conformal blocks, and it counts the ways you can fuse the particles together. And essentially, this detects the knots and the linking numbers of the topology, and in the deep infrared, the physics becomes topological. So for quantum states, the Hilbert space of Chern-Simons theory on a surface sigma is exactly the space of conformal blocks in two-dimensional conformal field theory. And so for a torus, the dimension of the Hilbert space would be k+1. And for a sphere with marked points, the dimension of the Hilbert space counts the ways to fuse particles or fusion rules. So in conclusion, the deep infrared or low energy physics becomes topology. And that's pretty much it. We've written the script of symplectic geometry, okay? That being classical mechanics itself. Forces are curvatures of connections. Particles are the representations of the Poincaré group, are irreducible representations. Mass and coupling itself are flows in the renormalization group. I forgot to add that. Quantum states are sections of line bundles, all right, or quantum or complex line bundles in configuration space. And state counting is just an index theory. How many quantum states are there? It's an index theory problem. And so this distinction between mathematics and physics really has vanished, right? Because all that's left really is structure, and physics has now become a theory of structure. In many ways, it's joined hands with mathematics. So this really completes our journey. And this, essentially, we started in chapter 1, the empty set. We built numbers, limit, the integral. Chapter 2, we built the invariant algebras, vectors, groups. Chapter 3, we bent the world into manifolds and sheaves. And here in chapter 4, we populated the world with fields and the forces of reality, and have shown that physics and mathematics are inherently married to each other. So we have unified all of physics with really a single geometric framework. And the laws of nature really aren't these arbitrary rules. They're inevitable consequences of topology, symmetry, and we've now really possessed an effective map of how to create effective theories of physics. And this is really the best that we've got so far. So we've written the script. We've really stripped the universe down to its bare mathematical bones. And we saw, that classical mechanics is not really about Newton's laws, right? It's about the geometry, essentially, of symplectic manifolds. And we saw, again, that forces are not vectors, right? They're curvatures, again, of principal bundles. Just trying to move down. So they're curvatures of principal bundles, and we saw that, again, particles themselves are not objects. They are just irreducible representations of the Poincaré group. And then using the index theorem, again, we were able to describe the topology of the phase space itself by just looking at the quantum states in the universe that's determined by the topology of the phase space. So again, this is great, but take a closer look at what we've built. We've constructed a beautiful crystalline cathedral, right? It's perfect, it's invariant, but it is very rigid. We assumed from everything that space-time is a smooth, differentiable manifold. We assumed that you can zoom infinitely far and see a flat plane. We assumed that points are fundamental and that trajectories are smooth curves. But nature disagrees, okay? Real physical paths are not smooth. They're jagged, they're non-differentiable, they're fractal, they have Brownian motion. There's real quantum fields are not functions, they're distributions that fluctuate wildly at every scale. And at the deepest level, the Planck scale, the very concept of space-time dissolves entirely. What we have built, though, is the geometric basis. Now what we need to do is face the analytical reality. We're going to leave the world of perfect smoothness, and we're going to introduce noise, roughness, and algebraic abstraction. So where we're going to go next, and where I want this channel to go next, and we'll see where this goes, but here's the top topics that we're going to try to look at. First, we need to look at more. We built the basics of stochastics, but we really need to break down the smoothness of everything that we've talked about. We need to realize that the deterministic world is just an average of chaotic stochastic reality. And we're going to talk about calculus, rough path theory, and discover that renormalization is the price we pay for ignoring the roughness of the world, right? We're going to talk about jet bundles and intrinsic geometry. We'll stop drawing equations on a manifold. In fact, we're just going to realize that the differential equation is the manifold. And we're going to talk more about differential equations as well. But we enter a world of jet spaces where symmetries will become geometric objects. And conservation laws will actually become closed forms. We'll talk about algebraic analysis. I'm looking at kind of my notes here of like what I want to talk about sometime after this gains a little bit of traction. But when functions fail us, we turn to algebra. So we'll talk about D-modules, microlocal analysis. And solutions are not numbers anymore here. We're going to start seeing solutions themselves as sheaves or just algebraic data that's living on a cotangent bundle. We can dissolve space-time entirely. And at the summit, we will ask the ultimate question, is space-time even real? Okay? Is space-time real? This is our underlying assumption of everything that we built so far, but it might not be. And we're going to explore twistor theory, where light rays are more fundamental than points. We'll look at the amplituhedron, where locality and unitarity are the emergent properties of some geometric volume and some Grassmannian algebra. We'll also see the world or the universe that we perceive is just a hologram, right, of a deeper algebraic geometry. So that's essentially what we'll be talking about next, but it will be in a different form, and that'll be the subject and exploration. All of those things I have written down, and those will be the subjects and explorations of shorter videos. But this is essentially the series that I wanted to, go through and walk through with you guys and reference and have categorize the subjects of this channel and the Discord server. So thank you guys for watching, and I will see you guys next time.